as we conclude the material that we're going to cover in an introductory course to differential equation. I want to take us all the way back to the first week of class, and we said that when we were trying to solve differential equations, there were different approaches. Okay? One was quantitative, one was analytic, and one was numerical. We haven't talked about the numerical way of doing it. Talked a lot about analytic and the different techniques. Talked a little bit about quantitative and looking at graphs and things of that nature. But now numerical. And so we want to finish up by looking at a couple of numerical ways of solving differential equations. The first one is called the Euler's method, and we did this back in calculus class. So if you have a differential equation, right? So it's a function of x and y, and we're given an initial value, starting point, x0, y0. The Euler's method was this repeated formula that the next y value was the last y value plus h, usually 0.1 or 0.05. It's an h percentage kind of an idea of the function. Here's the function at your last x value and your last y value. So y0 plus 1, so y1 would be y0, we'd be given that, plus h, whatever that is, times the function, whatever the function was, acting on x0, y0, and now you have y1. And then we can keep going, y2, y3, until we get a value that we can live with. For example, here is the Euler's method at 0.1, some function, y prime equals 2xy. Right? And they started out at 1, 1. So my first x value was 1, and then we were going to add 1/10. So my second x value would be 1/10, third x value, okay, down to 1.5. That's what we want to see. What are we at 1.5? So we have our first x value, they give me, and my first y value. So I plug those in, and we get 1 plus 0.1. X is 2xy, so 2 times 1 times 1, and you would get 1.2. And now we have y values. Now then you substitute that in, so 1.2 plus 0.1, a function of 2xy, so 2 times 1.1 and 1.2, and that'll give you my next y value. And you continue that, and 1.5, we're going to be about 2.9278. Now, the actual value, because this one we can evaluate, this is a separable differential equation, so we can solve that and get what the answer is. And you'll see that that's what your actual value is, and you're off 16%. When we go to 0.05, now the x values are increasing by 0.05, and you get the y values, putting them into the formula, using them, and you get 3.174. There's the actual value, so now you're off 9.8%, right? So in this case, at step 0.1, the 16% error, right? Step it up to 0.5, we get a little better error. And the problem is that one source of the error is the round off. Because when you do this into here, you're going to be rounding off as you go, and that rounding off is going to cause a bit of an error. That rounding off is going to cause a bit of an error as you go. But the process is not very good. In fact, Euler's method is almost never used in real life situations. Okay? There are errors that cause big problems. There are errors that cause big problems. So we need a better method. And so new and improved Euler's method. You know, when you get your advertisement and products and they come out with the new and improved. Well, that's what this is. The new and improved Euler's method. Again, here is the formula for the Euler's method. Here is the formula for the Euler's method. Again, we're going to do the same guy. Y prime equals 2xy, because we can actually evaluate that, starting at 1, 1. So the Euler's method, okay, the new and improved Euler's method, right, is that our next term is the last y term plus h, the function evaluated the last x and y term, plus the function at the next x, and then they call this y1 star, divided by 2. Where y1 star, right, is given by, it's basically an average idea when you're looking at y1 star, right? And you come up with a little better approximation, okay, called the improved Euler's method, commonly known as the improved Euler's method. Here's the terms. Just like the old one, the next y term is the last y term you have, h times the function evaluated at your last y term, x and y term, plus the function evaluated at the next x term, and y star, where y star is the Euler's method, the original Euler's method. So when you put that in and do that and keep pumping out answers. So here we go. We're given this function, 2xy, 1, 1. We want to do it at 0.5 and 0.05. So we'd figure out y star, which is the first y value, y1 star, first y value, plus 0.1, 2 times your first x and y, which are 1 and 1, you get 1.2. So then your y1 becomes y0 plus 0.1, and 2 times x0, y0, 2 times x1 prime, y prime over 2. So we can figure those all out, and we get 1.232. And then we do it again, and we do it again. And we do that, notice how much better do we improve. Same 5 steps, but notice we're now only 1.13% off, right? Relative error. What a difference between 1.13 and 16%. And if we do it in 0.05, notice you're only 0.31% off. So Euler's method, improved Euler's method. Again, neither of them are really the best methods to use. And so I want you to practice a couple of those and do some problems with it. Okay? But a better is called the Rutkutta method. Okay? The Rutkutta method. And the fourth order Rutkutta method, okay, as the name suggests, okay, there are different orders, right? And the Euler's method, improved Euler's method, you know, are related to this Rutkutta. But the RK4, as it's commonly referred to, is one of the best methods numerically. And here is what it is. Okay? If you want to find the next y term, when you know a y and an x term, right, it's equal to the next y term, so the second term is equal to the first y term, plus whatever h is over 6, k1, 2k2, 2k3, 2k4, where this is k1, k2, k3, k4. A little more work to do, but it's so much better. And with calculators and computers, these computations are fairly easy to do. Called the RK4 method. Okay? RK4 method. Do our same problem again. Do it, h is 0.1. Okay? I'm going to go to y of 1.5. Our derivative is 2xy. Our initial values are 1 and 1. And we're going to put them into this method. I'm going to put them into this method. So K1 is going to be the function at x0, y0. 2 times x0, y0, which are 1 and 1, so we get 2. K2 is the function 2 times the x value and the y value, where the x value is now x0 plus 1/2, 0.1, and the y value is your y0 plus 1/2, 0.1 times your new y value, which is 2. And so you'll get 2.31. K3 is the function 2 times the x value, and the x value is going to be x0, the original one, 1/2, 0.1. And the y value, the original y value, 1/2, okay, h, and then the last k value. And finally, the function at x0 plus 0.1 plus y0 times 0.1 times the previous k value. And so y1 is going to be y0, okay, which in our case here is 1. 0.1 over 6, k1, which was 2, 2 times k2, 2 times k3, k4, get 1.2367435. Okay, so we round it off. There's our next y value. And we do it again, and notice the same amount of steps, almost no error, slightly. 3.4902, 3.4904. Very little error. So when we look at these different methods, same problem, we've got x is 1, we're going at 0.1, so the next x term, 0.1, 1.1, 1.2, 1.3, 1.4, 1.5, so 5 times. When you use the Euler's method, after those 5 steps, you get 2.9278. Improved Euler's method, much better, 3.4509. The RK4 method, 3.4902, where here's the real value. Look how much more accurate in the same number of steps. If we do 0.5, again, Euler's more accurate, but it's still quite a bit off. The improved Euler is getting better, but notice the RK4 is almost dead on. Okay? And so the error, again, is there, but not much. So numerical method. It's a grind, it's a grind to grind it out, but once you have the formula, you just plug it in and do it and do it and do it. So I want to see the work. I want to see that you did this. I want you to work on these 2 sections, 9.1 and 9.2, along with 8.2, and that finishes up the material. So this week, you're finishing up the material in this course.